So today is going to be only 2D stuff. When we come back next time, we're going to be looking at surfaces in polar world and finding volumes. But today we're just going to focus on 2D stuff, so just finding area as polars. So sketch the polar curve r of theta equals cosine theta. So again, everything here is going to be in polar coordinates. And we remember that our polar coordinates are r comma theta. The first thing that's a little bit different than what we're used to is notice theta is the input here. The output gives you r. So it's kind of swapped from our x and y. Normally you plug in this guy and your output is this, but for polar it's actually switched. Theta, kind of y component, is now the input. So we can go ahead and the same thing we would do for a normal table for rectangular coordinates. Just grab a couple So just to understand how this works. So again, theta is now the input. So I can plug this into my function and I get r of 0, which is cosine of 0, and cosine of 0 is 1. So the coordinate is 1 comma 0. So again, be careful. It's kind of flipped from what we're used to. Here, this would be the cosine of pi over 2. Cosine of pi over 2 is 0. So that is the coordinate 0 comma pi over 2. So if we want to plot these points, don't forget these points exist in polar coordinates. So this is saying go out a distance of 1 and travel at an angle of 0. So that is 1 comma 0. This says go out a radius of 0, go to an angle of pi over 2, and it's still going to be right there because you still have a radius of 0. This is saying go to an angle of 0, then you've got a radius of -1.
But we need to see an animation to really kind of get the visual.
Oh, sorry, this should be 0. So if I go to pi, -1. So I have an angle of 0. And I'm going to start to kind of slowly increase theta. And this is exactly how I want you to visualize this. Instead of, rectangular, you're sweeping left to right for x. Theta, the input, is now being swept around by the green kind of circular piece that's going around counterclockwise. The output of the function gives you the radius, the r value, or the distance from the pole, from the origin. So this coordinate right here that you're seeing is if you have an angle of 0.47-ish in radians, and then it would give you an output of gives you an output of 0.89, meaning you are 0.89 away from the pole. So kind of just sweeping around. I get my pi over 2 comma 0. That was one of the points in the table. When you go to an angle of pi over 2, the radius is 0. So I've returned back to the pole. Starting to sweep over here now. This is where things get a little bit interesting for us. This is an angle of, whatever this might be over here or something, 3 pi over 4. But now the radius is pointing down in quadrant 4, which means you have a negative radius. So even though the angle opens up over here, it's supposed to give me how far from the pole I am. This is going to open out in the opposite direction. So notice my r of theta here, my output is a negative number. And I can sweep going all the way around like this. And when I land that pi, I trace out a full circle. If you kept going and you did this for 2 pi, then you just kind of traverse right around the same path. So this is one of those, this is kind of conceptual things for right now, trying to really grasp kind of what's happening. If I said r of theta equals 3, so that is just the curve r equals 3, what should this slowly be tracing out in my plane? Circle of radius 3. This is saying no matter where you go, it actually doesn't even matter what the angle is, you're always going to get a radius of 3. So you give me any angle you want, say 5 pi over 6. If you sweep out 5 pi over 6, then you go out with a radius of 3. If you go all the way to 3 pi over 2, you're going to go out a radius of 3. So this is kind of calling back on some exam 2 ideas of, no matter where you go, the radius is always 3. So you could also have some interesting things like 2 sine of theta. You can see just kind of interesting curves as you start to sweep out. That one is not exactly circular. Let's make this 3, this 1. And we start to get some negative radii. So we get some inner loop. And you can think of any kind of polar curve that you want. And you can see exactly how this traces out. Let's try another one. What if I said r of theta equals theta? Take 2 seconds, think about what that would look like. That's saying you go out to an angle of pi over 4, then the radius is pi over 4. You go out to an angle of pi over 2, and the radius is pi over 2.
So no matter where you go, the angle is the radius.
Big spiral.
Yes, that's exactly it. As you start to go out, as your radius, as your angle increases, the radius increases as well. So sweeping out, the angle gets bigger and bigger, the radius gets bigger and bigger. So I start to get this outward spiral. All right, so one of the first things I'll show you. This is not something that you would be quote unquote tested on or responsible for knowing, but just showing you, maybe we saw this before in a pre-calc class, some of these curves are quote unquote famous, have names. You can't see. So you can kind of just recognize noticeable ones, circles, cardioids. The cardioid idea is basically when the curve pulls back into the pole, you get this kind of point. If you've got like a one loop memeson, I think what's happening with their one loop is it's not exactly pointed, it's kind of flattened out. I'll show you that one does with us. You've got inner loops, Leibniz gates. These are just kind of curves that you should recognize and maybe you should hear them. You would never be asked to kind of match or be responsible for knowing the form of them. So for these polar functions, we are of course interested in both derivatives and integrals. So if I had that polar function, taking the derivative of something like 2 plus cosine theta taking the derivative, we would look at something like r prime of theta, or just using the other notation, dr d theta. I like this notation here because it's explaining it's how your radius is changing as you increase just a little bit of theta. So let's get 2 plus cosine theta. So this is saying if I increase theta just a little bit, what do we see is happening with the radius? Decreasing. So let's actually see that that's true. So here, my dr d theta, I'll write both notations, just. So my r prime of theta is equal to negative sine theta, which, just writing the same notation twice, writing the derivative twice with two different notations. And we'll say that's roughly an angle of 3 pi over 4. So if I want the derivative, you're going to take the derivative like normal, but now everything's just in terms of theta. All we're doing right now is just making sense of, what would the derivative mean? And again, I like this notation here. If you increase your angle just a little bit, then this is saying that your radius is decreasing because your derivative is negative. I'll go back to the animation one more time. If I've got 3 pi over 4, This is saying if we start to just increase just a little bit, just a hair, you can see that the radius gets kind of pulled in. And very similarly over here, if you were to find the derivative at something like 5 pi over 4, what do I notice about the radius? Increasing. Now, if you're kind of thinking about this like, well, you know, it is kind of moving to the right, moving to the left, moving down, how would I describe those? Then you can still write x coordinates and y coordinates. And all we would have to do is just remember our cheat sheet, our reference sheet, that x equals r cosine theta. That doesn't leave us from exam 2. So x equals r cosine theta. And don't forget that r is 2 plus cosine theta. So what does this equation give you? This says you give me the angle, but now instead of giving you how far out to go, I'm actually going to give you the honest to God x coordinate that we're familiar with. And very similarly, y equals r sine theta. So over here, Desmos doesn't like me calling it x of theta, so I'm going to call it f for x. So in Desmos. So going back to our animation over here, when we were traveling at 3 pi over 4, and we said, oh, it definitely looks like the radius is decreasing. But now ask yourself, how is the x coordinate changing? Is the x coordinate moving left, moving right?
Left.
Moving left. So that means that my dx d theta should be a negative number. So I'm going to run over to Desmos and just say, find f prime of 3 pi over 4. And sure enough, I do get a negative number. So now very similarly, coming back over here, so at this same angle, if I increase just a little bit, how is the y coordinate changing?
Going down.
Going down, decreasing. So again, over here, when I find g prime of 3 pi over 4, I should get a negative number. Check. Give me another angle to try this out. Say again? So now I want you guys to, how about this? Let me not even play the animation. So I have just the full image, not even an animation of it going around. We know pi over 2 is 90 degrees up there. So now ask yourself, what are the signs of dr d theta? At that angle, how is the radius changing? Ask yourself, what is the sign of dx d theta? What is the sign of dy d theta? So take 2 seconds, stare at that, see what we can come up with.
What does it, sorry, I just can't
Yeah,
really
yeah.
see it, what does it say, the 2 plus,
This one?
yeah.
2 plus cosine theta. So I took the r
Oh, okay.
and plugged it in over here. Alright, so when I go to pi over 2, angles coming around like this, how is the radius changing? Decreasing. Let's check it out. R prime of pi over 2 should be negative. There it is. How is the x coordinate changing at that time? Going to the left. So I should see a negative, check. And how is the y coordinate changing? Also going down. Now let's just kind of pick this point right here. We'll do an angle of 11 pi over 6. So stare at it for a second. Ask yourself the sign of dr d theta, dx d theta, dy d theta. You can use these kind of concentric circles to help guide you. If you're like, I can't really tell if the radius is increasing or decreasing, for me, I'm looking at this kind of gap here. And so, because this gap is getting smaller and smaller, I know that the radius is growing. So that means dr d theta has what kind of sign? Positive. Positive. So r prime of 11 pi over 6 should be positive, check. How is the x coordinate changing? Positive. And the y coordinate? Positive. 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 Sweet. So these are kind of the problem types that you would see. So one of the things over this long weekend that I'm going to ask is I'm going to post the the Desmo sheet to Blackboard. Just play around. You know, watch the animation go around. Try to really understand exactly how these polar functions work. So, you know, what are things you would actually be responsible for? Would be questions like this. Consider the function r of theta equals 3 minus 4 sine theta. Write an equation for the y-coordinate in terms of theta. All we have to remember is y equals r sine theta. So my y-coordinate in terms of theta is going to be r times sine theta. Where r itself is 3 minus 4 sine theta. So very similarly, it could ask you something like, what is the y-coordinate when theta is pi over 6? Then you would write y equals something in terms of theta, then you just plug in pi over 6. Questions on it? B says, is the radius increasing or decreasing at pi over 6? Now we need to be careful here. There are different things we could ask if it's increasing or decreasing. The x-coordinate, the y-coordinate, and the radius of the r value. Is the radius increasing or decreasing? That is dr d theta. How is the radius changing in terms of theta? I can just take the derivative of my equation up here. The derivative of sine is cosine, so I get negative 4 cosine theta. That means that dr d theta at pi over 6 I get a negative number, so the radius is decreasing. Questions on B? C says, is the x-coordinate increasing or decreasing? So this is going to be one of those, it'll say on the exam, or it'll be in the Desmo section. It'll be a calculator question. Is the x-coordinate increasing or decreasing? So I'm going to kind of almost combine both of these ideas. First, I'm going to write an equation for the x-coordinate, just remembering that x equals r cosine theta. So I want x prime of pi over 6. So now, you might say, well, why is that a calculator question? Can't you take the derivative, plug in pi over 6? Sure, But what would I have to do to take the derivative of this? Yeah, you'd have to do a product rule. It doesn't mean it's impossible, we can do it, but we're more interested in the actual result. So what we would do is just run over to Desmos. You can type things in terms of theta, or it's still a function if you just want to write things in terms of x. Oh, we got 3 minus 4 cosine theta.
Yeah, for sine theta.
Three sine.
Say one more time.
3 minus 4 sine theta.
So I want the derivative f prime at pi over 6. All right. Let's make sense of this one then. What if I had r of theta equals 8? That means dr d theta equals 0. Why does that make sense for our animation?
The radius is not changing, it's just circle radius 8.
I agree. The radius itself, how far from the pole, never changes. It's always traveling with the same radius. So this is kind of what a derivative of 0 function looks like in polar form. Your radius never changes, so it's circle. I'm now trying to think of a function whose derivative is always positive, like r of theta equals theta. Your derivative is 1. So that means no matter where you go, your radius is always increasing. I want to see some interesting ones. If I do r of theta is 1 over theta. So if my angle kind of increases forever, I've got 1 over almost infinity. That means as I traverse, as I wrap around, 1 over infinity is going to get closer and closer to 0. So I'm traveling closer and closer and closer to the pole. All right, let's look at some integrals. So if I want the area of a polar function, then this is going to be the formula that we want on our reference sheet. And I'll show where this comes from in just a second. What does that visually look like? If you have some sort of polar curve being traced out, then I want the area bound between the pole and your curve. Between now two angles, from theta equals alpha, sweeping out to theta equals beta. So you get this almost kind of wedge piece. And finding the integral would give you the area of this kind of sector. And that's actually going to motivate exactly where that formula comes from. So for rectangular, we would draw rectangles under curves to approximate the area. Here, we can approximate it using a sector of a circle. Where that's going to have some angle that's opening. You won't be responsible for reproducing, I'm just kind of showing where this formula comes from. So if I imagine that this is kind of an entire circle here, and I want the area of just that sector, it's going to be the area of the circle, pi r squared, but I want some teeny fraction of it. The fraction that is the angle out of the entire angle, which is either 360 or, if we're in radians, and 2 pi. Cleaning this up a bit, pi's cancel out. I'm left with 1/2 theta r squared. We're looking closer and closer. And now, just like what we did with Riemann sums in Calc 1, you just want the width of the rectangle to be infinitely tiny, so a dx. Well, here I want the kind of angle to be super tiny, and I want a super thin wedge, so I want a d theta. And then we just add all of those wedges together from an angle of theta equals alpha, all the way up to theta equals b. Again, not responsible for producing this. It's just an interesting formula that kind of, we wonder, like, why? Where does that even come from? This is where it's coming from. So let's go ahead and first practice this. Using a known area. So in some of these more complicated polar curves, you would have a Desmos section, you would have Desmos in front of you. Some of the more basic ones, or if I gave you a sketch, we should be able to think of how this works. So first, just sketch r of theta equals 4 from 0 to pi over 2. So help me out, what does r of theta equals 4 look like? It's a circle. No matter where you go, the radius is 4. And it's saying plot this from an angle of 0 to an angle of pi over 2. So this is maybe what the actual question itself would look like. You walk up to the exam, it gives you maybe a graph or an equation. Let R be the region bound in the first quadrant by R of theta equals 4. So I'm in the first quadrant, bound by R of theta equals 4. That is just a circle. Find the area of R. Now, we know some quick geometry of how we can get that. We're going to first use our area of polar functions formula, verify it works, using geometry. So the area is going to be 1/2 the definite integral from A to B from an angle of 0 to an angle of pi over 2. R of theta is 4. Don't forget the squared detail. So this is the area here, but we will work that out. Antiderivative of 4 squared with respect to theta is 4 squared theta.
You want to call it 16, that's fine.
Plug in pi over 2 minus plug in 0. So I'm getting that the area of the sector should be 4 pi. Let's just use some known geometry here. If I've got a circle with radius 4, that's pi times r squared, or 16 pi. Why is that not identical yet? Yeah, you only want 1/4 of the circle. Divided by 4, you get 4. I will let you know, these are that's the only integral that you can do by hand for these. The rest of them that involve sines and cosines, when you start talking about, cosine squared, we don't have a clean antiderivative of cosine squared. Now you can probably rip out a trig textbook and find some identities, but I'll let you know anytime you see a definite integral for these polar functions, it's going to say use a calculator to find the area. So you're more responsible for the setup than plugging this in the gaps.
Sorry, I didn't remain in this.
Yep.
Where the pi and the squared, where that from?
This one? So here I'm using geometry to verify.
Oh,
So just area of a circle.
okay.
All right, let's try another one. So again, anytime you're asked to find the area here, the question might just say, write the definite integral. So you're just gonna write this, that's your answer, that is an answer. Or you use a calculator to then plug in those values. So I think kind of the format, it's not too bad. You got 1/2 the definite integral, whatever your function is, just don't forget the squared, eat it. The only thing that's, I'll say it again, the only thing that's tricky about these problems are the limits of integration. We have to be phenomenal when it comes to angles. Not just like, simple quadrants like this, but being able to find angles, which we'll see in a second, is gonna be the hard part. And here I'm integrating from what to what?
Pi to 3 pi over 2.
Pi to 3 pi over 2. Now we just run over to Desmos. Questions? All right, so we've got interesting polar curves that have these pedal properties. I'll go ahead and just play an animation to see exactly how this is happening. Once you start getting over here, you get negative radii. So it doesn't actually like draw out pedal, 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 pedal. It kind of loops around, then starts to kind of go around as you have negative angles. Very common question is it could ask you to find the area inside one of the pedals, or it could say find the total area of all of the pedals. And if you want the total area of all of the pedals, you're going to find the area of one of them and multiply by however many pedals you have, in this case 4. The only thing that's tricky, and we might be able to tell based on the animation, but if I gave you just the static image, it's kind of hard to tell where a pedal starts and ends. Just remember, the pedal starts and ends when the radius is 0. Because a radius of 0 means you've returned back to the pole. So we're going to have to solve this equation for theta. We want to find when the radius equals 0. So just to make sure, Why are we solving for the radius equals 0? I want where a pedal starts and ends. And the way that the geometry of the system works is a radius of 0 means you're at the pole. So if I'm sweeping out, I'm drawing a pedal, I have finished the pedal when the radius equals 0 again. So to solve for where that happens, we can set the equation equal to 0. If I want to solve for where sine of 2 theta equals 0, kind of covering that up for a second, where does the sine equal 0?
Pi in negative, what, pi and 0.
I agree. So the sine of something equals 0, that means the inside had to have been 0, had to have been pi. Are those the only ones? No, they go on forever. But just inside the first unit circle. That means theta was 0, and theta was pi over 2. Some of the ones like this one you probably could have done by inspection. Others, I'll let you know you can't. You would have to just work it out. Now, if we're wondering, but it looks like it would return to the pole more than 2 times. Yes, don't forget, these are only the first 2. Why? I'm only trying to find one of the pedals. Do I still have you guys here? So now, the area of one of the pedals is 1/2 the definite integral from 0 to pi over 2. So if you want all 4 pedals, then you can just multiply by 4. And 4 times 1/2 is 2.
Maybe, do we have to solve that? I mean, like 0, right?
What if we said,
Because this is another way the question would be worded, right, but do not evaluate.
say it one more time? You said like if it wanted just 2 of them? Then you just multiply this by 2. Then you multiply this by 3. So you get a 3 halves.
Okay. 4 has 2. 4 pairs. Okay. 0.39. Two outside.
One of the other things that we did in Calc 2 is find the areas between curves. And you can do the same idea in polar.
That'll be the fourth point here.
Thank you. So we can find areas between polar curves. So I have it on Desmos, I have the true kind of pretty picture here. And I've tried to sketch it on the board. So you get this almost, every time I see this, this always reminds me of like the Grinch, and like the Doctor Who stuff. So areas between curves, in Calc 2, we did top curve minus bottom curve. For polar, you're gonna do outer minus inner. So you're not asking yourself anymore like top curve, bottom curve. You're asking yourself outer function, inner function. The other thing, notation-wise, if you've got multiple equations running around, they can't both be r of theta. So sometimes you'll see like r sub 1 of theta, r sub 2 of theta, or like maybe a capital R, little r, big R. So last time when we were doing volumes for general regions, you saw me drawing vertical and horizontal lines. This time, to help my brain figure out what's happening, I'm going to draw a line from the pole. And now when you're doing outer minus inner, it's the farther one from the pole minus the inner curve from the pole. If this was just the image that was given to you on the test, but it didn't tell you which is which, it's a very common problem type to see this. One of them is a polar curve. One of them is just a circle. You're responsible for knowing that, okay, I know the circular one is the perfect circle. This is r equals 3. And the one that looks kind of, curved or bowed in some areas is going to be this one. So it might not explicitly tell you in words which one the outer one is. So here, my area is going to be 1/2 the definite integral of something squared. What is the outermost function here? 3. Minus the innermost function, don't forget you're subtracting all of that. Squared. All I'm left with now, my limits of integration. However, do we have questions on just this? If you've got two curves, you want the area bounded by bounded between two curves. It's gonna be the same idea. In Calc 2, we did top minus bottom. Polar, you're gonna do outer minus inner. So to help you, I would just draw something from the pole. This is now what you're using to judge outer and inner. The outer piece is the one that is farther away. And I am integrating from what to what?
Pi over 2 to 2 pi.
Sweet. 3 pi over 2 to 2 pi.
You explain that to our limits?
Yeah.
Why is it outer minus inner squared? I'm just.
So what is this distance here? This radius is going to be how far away I am here minus how far I am away here. This gives you your new radius, the difference between those two.
So everything we're given like in the fourth quadrant, that basically tells us what our limit is gonna be.
I don't want to say always, but I'm having a hard time thinking of, maybe it could intersect and come at a point.
Wanna tell us
Before
how
that.
it could be done,
I'm having a hard time thinking of those problems. I think it's safe to say, if you're in that quadrant. All right, do you have a project?
Who's doing the project? What was it?
All right, so again-
Over 2.
Say again?
Why the 3 pi over 2 over 2 pi? I'm still.
So I'm always sweeping counterclockwise.
Uh-huh.
So this is an angle of 3 pi over 2, sweeping out to 2 pi.
Okay. Okay.
All right, go ahead and just open the project. The copier didn't do its job. Does someone have a pencil? No. All right, so opening it up. These should be the shaded regions. I'm going to kind of mark heavy down and help us out.
Okay.
Can you go back to the?
Yep.
So the whole thing is shaded?
Shaded.
For this kind of seashell looking
Yeah.
one, yes.
Shaded. Shaded. Okay.
All right, number 4, it's this region here.
Nice.
What? That little thing?
And it goes out, and it eventually looks like a swirl.
Fibonacci spiral?
Vivid
Yeah,
that.
Fibonacci spiral.
Vivid.
I would have never gotten it.
Yeah.
I would have never.
Now.
That's why you guys need to take college geometry.
I actually just deleted it on my group.
Alright, did everyone get a chance to see all the different shading here?
What was 2D?
Instead of advanced.
The whole thing.
Doing something. This is.
It's.
What class would you really recommend someone take?
History.
When is that one due out?
It's in the spring. We did it last year, so it'll be spring of 26.
I'll be doing that. I'll be there.
Wait, I was trying to.
History of math.
I was trying to put it in a different schedule, but I don't think I moved it. So I'm not gonna take it.
What about in general now? What's the class?
Alright, so this is kind of a longer project. It is a lot kind of thrown at us all at once. We're trying to do Calc 3 stuff, so I do want to make sure that we've at least seen the 2D stuff and are fluent with it before we move to 3D. Retake tomorrow. Did we say what time?
12:30.
12:30 in office.
Yeah, I was gonna say something, yeah, I forgot.
So, we might have to push back to 1. I have a class at 2, however, you guys are more than welcome to still take however long. So, we'll meet at 1 in my office, and if you guys need longer than that, that's perfectly fine.
Then it becomes a group test. I didn't say that.
Oh, yeah, I have a class at 3:30. Email me when you're done, and I'll tell you. Alright, any questions? Don't forget, there's no class Friday, so I will see
Oh,
everyone
yeah,
next
that's
week.
right.
Harder to.
That is wonderful,
I don't think it's good, but like, yeah, I'm not.
wonderful.
Five